In this session, we are going to see about polynomial co-fitting. In a very simple Python code, you will be able to understand, what is polynomial co-fitting and what are all the basic, the models are, why we are going for polynomial co-fitting, first of all. In a very simple manner, I'm just going to explain you how this code, especially we have a code and already and it has run, and I will explain you how this topic is going to be. So first of all, what is the agenda for today's session? This is the agenda: how to create a sine wave, and these are all the topics: how to create a sine wave and how to create a Gaussian noise, create noisy sine wave by adding Gaussian noise in it, sample 10 points from a noisy sine wave and fit a curve, and that can be characterized by polynomial functions. Use polynomial curve fitting with different orders of polynomial to see underfitting on and overfitting problem. So basically we have set of data points and we are going to analyze using sine wave, and I'm taking that the 100 the number of points as 100 over here. This is the n underscore points equal to 100. So before that, you just in Python environment, this is the this environment is a visual code environment. This is the default I have set in my system. So import numpy as np and n underscore points, I'm just giving the variable as a value 100. This is the number of points I'm taking in to consider. So x is equal to np dot linspace 0, 1, and within 0, 1, what are all the points I have, and it will get displayed over here. See, you can see all the 100 points over here. Okay, between 0 and 1. So you see, this is the sample n points, and num equal to n points. I'm just assigning num equal to n points. So np dot sine wave, I'm just creating the sine wave 2 into np dot pi into x. So I'm just giving the x value to pi and 2 into np. So this is the np of line space and 0, 1. Okay, so first we will create the sine wave, so that after getting the sine wave, we'll be able to understand this is the sample of 100 points, and this is the plot using this matplot library, because without that you will not be able to see this graph over here. So this is the very simple graph, and I'm just creating the color differentiation. It's just a green. So this is a simple sine wave. I'm just saying with 100 points, this is distributed over like this, right? I think you will all be able to follow this very simple code in Python environment. Okay, so this is a plot, and you just take all the things, very matplot library from the Python libraries. Okay, and how to create a Gaussian noise. So actually noise, what is called noise, what is Gaussian noise? Because since we have 100 points over here, these 100 points in this graph just distributed among, because it starts from 0 and 1, right? So between these two values, the 100 values are there, and how we will be able to see how it has been distributed between the x and z, x-axis and the z-axis. So since we are dealing with polynomial thing, we don't have a y-axis. We just convert this in a z-axis. Okay, so this is x and this is z, and you can see the sine wave now. And now we are going to create a simple code for Gaussian noise, so that we'll be able to understand what is the noise between these two values, 0 and 1, and the sample number is 100. Okay, so now I think you will be able to follow if you see this. Yes, see, this is a noise between 0 and 1 value in this Gaussian. This is called the Gaussian noise. So this is the plot x comma, this is ETA for Gaussian noise to find out. This is the default, I mean, this is the code for the Gaussian noise. See, here ETA is 0.4 into this numpy and then random, the normal, and it's just a standard and mean and standard deviation. This is, you can just see over here, the Gaussian noise of mean 0 and standard deviation 1. Between 0 and 1, what is the average distribution of the values between these two things? This is very simple. So I mean, we will be able to, I mean, somehow we got the 100 data points, but we don't know how it has been distributed, or we couldn't, or we wouldn't be able to visualize, right? That is why we are just applying some kind of a graphical thing, so that how the distribution coming across. So this is what it is, mainly called, or mainly for this kind of a graphical representations. So we'll get to know how it has been, how the distribution happening across the values. So this is the noise. So first we have seen the sine wave. Now you just see this Gaussian noise. I mean, what is the noise between these two values based on, this is the general, I mean, the default, the syntax for finding the Gaussian noise. Okay. And then the noise is sine wave over, I mean, you can see. And now I'm going to add the Z value plus ETA. ETA is my Gaussian and Z is my sine wave, right? Here is Z. Here is Z. So I'm going to create the third graph, how it has been distributed, how the, the plot has been, the noise is sine wave, how it could be, because I'm just in this graph, I'm just seeing the noise, but I wanted to see how my sine wave is within this, right? So this is the thing. So this is the, again, formula. Z is the original sine signal and T is the noisy signal. Okay. So already, so we are deriving T, the noisy signal, across these 100 values. You can see it is very basic thing in this, the statistical thing. Okay, it is especially in polynomial, because this, we wanted to understand the polynomial distribution in this section. So that is why we will be, the first procedure is to get the sine wave between the values, and then the distribute, I mean, how the noise between the values. And now we have just integrated both the values, the sine wave and the noisy signal, okay, with this plot and also these legend values, right? So these are all the codes and you can use for getting this graph. Now I'm going to analyze I'm just going to take 10 points randomly from a noisy sine wave. From this, I'm going to take a 10 values, because I don't, I mean, because it is 100 values, 100 sample points, it has been distributed across, but I wanted to find something out of it, how my polynomial, or the value of the polynomial, how it is going to be, how, what is the least, I mean, yes, I'll coming to the point why we, I mean, if I go to the polynomial curve distribution, curve fitting, then you'll be able to understand what is the point I'm coming for. Okay, right. So just keep in mind, as of now, I'm just taking 10 points from this value, not 100 all the values. I'm just going to take 10, only 10 points. So the same thing again, I'm just going to create the X and T value, not the Z value, because already we found based on the Z value, we got the T value, right? So based on that, I'm going to take the lens space and also the sine wave and the noise. Add noise of mean 0 and SD of 1. Okay, I'm just again the same kind of thing. See, just from this 100 sample points, I'm just taking only the 10 points. Very simple. For that, we have written this code. Very simple. So you got it right? Okay. Now, so this is the 10 points I have taken, and these are all the, this is the sine wave of mine. So just keep in mind, that's it. Now we are coming to our problem. So what is our polynomial curve fitting in these data points with this sine wave and this noise? Okay, what is it? Okay, so I'm going to input the x value and the t value with this 10 points, right? And the most important thing is the coefficient of the value. And also I'm just going for the order, because then only I will be, I mean, if I'm going to take the 3 order or 6 order or 9 order, I'm just going to have the sample now. And also I'm going to take a coefficient of those values, right? So this is the thing. And this is the coefficient I wanted to find out. The coefficient is equal to, this is the fitting this polynomial and finding coefficients. This is the formula I'm just going to give it, and m equal to 3, that is the order I'm giving, right? And before that, while coming to polynomial curve fitting, there is one important thing that is called the polynomial formula. So what is that, the error find, I mean, what is the least error I'm finding it? That is the thing. So I will come those kind of things, at the end of the session. Okay, just wait for a moment. So I will show you. Right, so this polynomial curve fitting, and I'm just going to find out the coefficients are, these are all the coefficient of the value, the 3 orders, only 3 value I'm just giving it. And with respect to this 2 variables, this is a polyfit and poly LD is the I mean variables, and I'm just giving the value, right? So if you wanted to find out the polynomial curve, so you have to give this polyfit and poly LD, poly 1D, I guess. Yeah, poly 1D, not LD, sorry. Right, so this is the one, and yes, this is the training data and also the model with m equal to 3. See, so this is my polynomial curve, right, with the order m is equal to 3. So these are all the 3 values. I mean, these are all the values. I mean, with the order of 3, I'm getting this thing. So what is it? Basically, this is close to this, and but this value is, more, it has a too much difference, and but this is somewhat closer, and this is somewhat closer, and this is very close. And we need to find out again what is the maximum error between these values. So what is that? What does it mean? The mean square error, it is, that is called MSE. This is the formula, 0.5 star of np dot sum of the y underscore PRED hyphen t, I mean, and t underscore sample star 2. So this is for the training data, because we have 10 values of training data, and I wanted to find out those errors, right? This is the error, 0.1. Okay, so this is fine, 0.100. So this model, I mean, this is the error and the percentage of error. So this is the least error with the order 3. And so this model might find, but we need to compare with the other orders as well, right? So I mean, for comparison, we need to have more than 3 sets of data comparisons. So we'll just see how the next set is. Check the output of new data points about the new n equal to 5, and then these are all the new values, and I want to find out ETA of the noise, right, Gaussian noise, and then I wanted to put a plot about the polynomial thing, and my training data is there, my model is a polynomial, and also I have a testing data, right? So you can see the blue is the training data, and the model is polynomial distribution, polynomial curve fitting, how the curve is rightly fit, or is it over fit, or it is under fit, or close to that fit. So this is what our aim is. Okay, so why we are, I mean, even though we have some kind of a relationship with the linear distribution or other models, but we need to find out the polynomial thing so that it is very, very close to the error. That means the error is very less. It is not more, it is less. It is comparatively less for other, compared to other data. Maybe because we have a training data and also tested data, and we between those we are just finding out on the basis of the order, right? So now it has the value of 0.28. The other five data points, I mean the testing data is 1, the green is testing data, 2, 3, 4, 5. It has a different value, right? And it is 0.28. It's somewhat, the error rate is higher than the first one what we had, right? That is 0.1, now it is 0.28. This is greater, this is greater error. It's going up, the error is more. Now we are exactly coming to the curve fitting, right? Fitting this polynomial and finding coefficients, and third order, and also the ninth one, I mean the fifth, and the other thing. Okay, because we found out the third order and how was it, and we're now going to find out the ninth order, and everything is put together in a single graph. So this is what this polynomial this code it meant for. So after running this code, we are getting like this. Okay, so the order is 3 and 9. So use polynomial curve fitting with different orders of polynomial to see underfitting, it's 0, and overfitting is 9. So the problem is, if we are going above and above the order, we are getting, so you can see over here, so training data and fitting with order equal to 0, m equal to 0, this is m equal to 1, and this is m equal to 3, and m is equal to 9. So more or less this m is equal to 9, all the values this curve fits, right? It's kind of overfit, right? But 3, it's fine because it is underfit, but it is, I mean, it's not like m equal to 0. This is underfit because it is, the coefficient is not close to the value, and the error rate is more because there are a lot of deviations, right? But again, m equal to 1, the same similar thing. M equal to 3, this is somewhat the right model for our problem. So this is what we have to go through it, until Wm. So we have seen the m is equal to 0, 3, and 9, right? This is the m order. So we are finding out the coefficients of all the things with respect to all the values over here. So this is the ultimate thing we have already seen, right? So the error rate of, which is minimum, it is not overfitting the curve, it is not the very, very underfitting the curve. What would be the right fitting for our model? So this is the thing we are, so m equal to 3 is more or less, it's just a right fit for our model. So this is overfit. So this m equal to 9 is overfit, and the value of this is, the probability value is it's more than 0.3 or 0.4, but this is really uh, uh, more or less equal to the very less error rate. So the going for polynomial thing, to find out which one is the getting the minimal error rate.